Welcome back after the lunch break. We now resume with our afternoon session, beginning with Professor Gautam Makwana's lecture on deep learning fundamentals. Over to you, Professor Gautam.
Thank you very much. Now, today is the second day of the Gyan course, and lecture number 8, Deep Learning Fundamental. Before this lecture, we have completed the many aspects of the AI and the machine learning aspect and the algorithm and the different case studies also. And now in this lecture, we just discuss the introduction and the difference between the AI, ML, and DL, how the deep learning is evolved, and what are the geometrical interpretation of the deep learning, and how the deep learning is the reverse of the Ockham wedges, and finality regarding the process flow and the AWNS, and the different kind of the deep learning. We will discuss the AWN, LSTM, and RNN, and also I will discuss the use cases. If the time permit, then I will talk the hydrologic system of the odd man reverse watershed regarding the overfitting, calibration, validation, and the out of the sample prediction use cases. And the last is the convolution neural networks. So before starting this my session, I just acknowledge all the contributors mentioned here, mainly the Saman Rajavi, who give the very good explain the deep learning foundations, fundamental in the other aspect of the deep learning. Now, this is the deep learning, machine learning, and machine learning is the subset of the AI, and all deep learning are the machine learnings, and all machine learning are the AI, but the reverse is not true. Okay, so this is just idea about the deep learning, machine learning, and how it can be the conceptualize the machine learning, deep learning, and the AI. Okay, so the main difference is the multi-layer process techniques, and the machine learning is the your data-driven method. Okay, now this is the for the machine learning point of view. There are the two kind of the things: training and the interference. Okay, the training is the based on your data set, the model will train, and it will calculate the loss functions. And depending upon the if the and based on this training, we can classify the any data set either in the classification or in the label, and based on this loss function, we can get the regarding the about the accuracy or some kind of the performance parameter of the machine learning can be identified, and where the interference will be the after the training. If you give the unseen data to the your trained model and how it is behave, so that is known as your interference. Okay, so this is the things happen in the your machine learning, and the basic difference between the AI and ML and DL. So this AI is focused on the creating the machine to perform the tasks that require the human intelligence, where the machine learning involves the training algorithms to learn a pattern from the data and make decisions based on the training. And in the deep learning, uses the neural networks with the many layers to model a complex pattern in the large data set. AI will cover the all ML, DL, NLP, and robotics, and machine learning will include the algorithm for the learning from the data, and deep learning will the neural networks based algorithm. AI development time to be long due to the diverse application. In the machine learning, it is a moderate development time, and depending on the your data and algorithms. And in the case of the deep learning, a long development time due to the complexity and the large data requirement. AI having the low interpretability, machine learning having the higher interpretability, and deep learning is having the low interpretability regarding the your because of the complex brain blocks in the your deep learning case. Regarding the accuracy of the model. In the AI, accuracy are varies. In the machine learning, it is the moderate accuracy, and the deep learning it is the high accuracies. Now, to understand the deep learnings, if you think about this 10 question, then you are able to understand what is a deep learning actually. Okay. The first is the how is the DL and how did it evolve from the ANN, artificial neural networks. How can we interpret the internal functioning of the DLs? Third question is that does a DL abandon the Occam result or the principle of the parsimony that we will discuss in the my part? And why is a DL considered the superior to the other type of the ML? How can DL account for the memory and the time dependency? How to DL and process-based model compare in the calibration and validation, and which one may be more trustworthy? What is the value of the often ignored domain knowledge in the DL, and why may DL suffer from this ignorance? Why is a DL essentially different from the process-based modeling? And what are the existing approaches to the bridging the DL and the process-based modeling? What can we learn from the prominent DL application, such as the gaming and the stock market? So if you address this 10 question, then you are able to understand all the conceptually what is the deep learning actually is. Okay. Now, in the 1957, the Frank Rosenberg invented the concept about the percept clause. Okay, and the percept form is given by the this part of the your figure that it can be represented by the sigma I equal to 0 to d wi and xi, where the xi are the input and wi are the weight of the input. Okay, and here this wi and xi are the linear combination of the input. This refers to the your weight, and the value of the weight and the b is your bias. So this is your depending upon the value of the input and value of the bias. This summation will be the linear functions. Okay. Now at this case of this linear functions. Now what is the here? What is the issue here? This is the non-area concept about the perceptron that having the linear combination of the input space and the weight. Now the input is anything and the weight can be the anything. So at the time this value of the summation may be the from the infinite to plus infinite. Okay, it is very having the large value of the your output of the one perceptron. So now how to regulate? Because in the computer we cannot go for the infinite and the finite. So for this case, we have to normalize. We have to normalize the your this output of the perceptrons. So this for this case, it is a we require the activation functions. We require the activation function that will normalize your output of the this perceptron into the some range. This range will be there from the -1 to 1, or maybe it is a 0 to 1s. Okay, so in this case, whatever the your linear combination of the inputs space and the weight are normalized into the between the -1 to 1 or maybe the into the 0 to 1, depending upon the type of the activation functions. Okay, so here, what is the 0 to 1? 0 to 1 is what? In the probability distributions. Okay, the maximum is the 1 probability and minimum is the 0. So if you mapping your input space or linear combination of the this perceptron concept, then you are adding the concept about the probabilities. It is after your activation function that your input space and the weight are be mapping to the probability distribution between the 0 to 1. So that is a function of your activation function that will convert your input space into your probability distributions. Okay, so this is the concept about the perceptron, or I can say it is the neutrons, and the dimension of this perceptron is depending upon the number of the tunable parameters. Here in this figure, the number of the tunable parameter is the weight. Okay, if the input is the phi, then the number of the weight is the phi. And then another parameter of the tunable parameter is the bias. Okay, so this is the your number of the tunable parameter for the this case is depend upon the number of the inputs plus the one bias. Okay, so this is your D plus D weight and the one bias. So if you increase the input, then the your tunable parameter will be the increase. Now there are the many activation function. One of the popular is the your sigmoidal. Okay, one of the sigmoidal activation function, then ReLU function, soft max function, and the 10 edge function are the one of the activation function in the your deep learning. Now, what are this actually? Now, these are the type of the your activation function. If you look at this sigmoid, this is your sigmoid activation function. So, depending upon the output of the linear combination of the input space and weight, it is vary -1 minus infinite to plus infinite. So what is happening here? It is a mapping from the 0 to 1 only. 0 to 1. Okay. So whatever the your linear combination of the input space and the weight after the your pulse spawn of the output will map into the 0 to 1. And this will adding the my I can say it is a convergence of the my pulse spawn. So there are two cases. Either it is diverse or it may be the converse. If it is diverse, then there is no control. So to make the conversion of the my perceptron, we have to use the activation functions. Okay, and there are the many others kind of the this ELU. Okay, so here sigmoidal is having the 0 to 1 only, 0 to 1. But here ELU having the minus from the -1 to 0. The negative part of the your linear combination will come in the picture in the case of the ELU, but in the sigmoid, it will not consider the negative. It is a, I can say, rectified. Okay. At the same way, there is a ReLU function also. Okay. So here all are the rectified. Rectify the your input space if it is the negative. This is your linear case, and this is your 10 8 sigmoid from the -1 to +1. So these are the activation function used in the your output of the your perceptron to make the converse the your perceptron in between the 0 to 1. Okay. Now here input. Okay, but how it can be put into the your perceptron cases here. Okay, so in the linear, it is a quadratic equations. Okay, so there are the two way we can solve the issue if the my input are the non-linears. Okay, to employ the linear regression by arriving the term to be form of the quadratic in the equations. Okay, and this option requires to specify the form of the non-linearity which is not typically known as the prior, requires the extensive trial and error. Okay, so if you just put into the that equation, this equation, the non-linearity, it requires the trial and error method to find out the find out your output y. Okay, now the second way to deal with the your non-linear input. Okay, to combine the perceptron both in the parallel and the series. So it is a single perceptron, but making the combination of the series and the parallel. Then it will add the my, I can add the non-linearity into the my this concept about the perceptron, and this is non-linear multi-layer perceptrons MLP. Okay, so here in this case, this is your single perceptrons. Now it is coming the multiples. Okay, either in the series or either in the parallel. Okay, so because of the non-linearity of the your input. Okay, so for this case, this is non-linear multi-layer perceptrons. Okay, so here a number of the input layer, number of the hidden layer, and the number of the output layer. And this one circle will indicate the one perceptrons or one neuron. Okay. So here what happened? The number of the parameters, number of the tunable parameters. Okay. So here the depending upon the number of the input and number of the nucleons. Okay. So for this case, the first layer of the nucleon, it is a D into this is what happened here. There are 4 input, 2 hidden layer, and the 3 outputs. This is the case about the 4 input, 2 hidden layer, and the 1 output layer. So the first layer of the nucleon, it is a D dot N1 weight and the N1 bias. N1 is the number of the neutron in the hidden layer. At the same way, in the second layer, N1 and N2 number of the neutron are the N2, and here it is the N1 to N1 into N2 weight and N2 bias. At the same way, in the last layer, depending upon the number of the hidden layer in the second last layer and the last layers. Okay, this is known as your ND weight and the ND minus 1 and ND weight into the second last and the last layer of the your multi layer perceptrons. And here, in this case, number of the tuning parameters. Okay, in your first case, the weight are the my tuning parameter are number. It is depending upon the how many layers and how many number of the neutrons. Okay, so it is for this case the summation of all this parameter will be the my final tuning parameter for a given given multi-layer perceptrons. Okay, now there is another concept about the hyperparameter. What is the hyperparameter? Hyperparameter is the known as your total number of the layer in the MLP and the number of the neutron in the each layers. Number of the this is the how many weight and how many biases in the multi-layer. That is the your parameters. And hyperparameter is known as your number of the layer in the MLP and the number of the neutron in the each layer are the known as your hyperparameter to be specified by the users. So it is a more parameter are here as compared to the in the case of the your machine learning point of view, this one. And the second, the choice of the activation function is each layer is also important. Choice of the activation functions. Okay, depending upon this activation function, every layer having the one particular activation function to diverse the output of the each perceptrons. Okay. Now, in the first case, in here, the weight are fixed. Weight are having the update is a fixed values. Okay, but in this case, to solve this to get the field about the ANN, the field about the ANN. Okay, so there is the one back propagations. What is the back propagation? That will update the weight. It will calculate the gradients at every equation, and based on the gradient, the weight are update. Weight are update. The back propagation calculate the gradient of the loss function, and with respect to the weight using the chain rule, and then the update the weight according to the gradients. The every iterations, the loss function will be the calculated by this equation, where the yjk is the output of the neutron j in the output layer when the network is forced with the input data sample k, and the tjk is the respective data target, and m is the size of the training data, and nd is the number of the neutron in the output layer. So depending upon the this loss function, so every loss function, this back propagation will calculate the gradients of the loss function, and the gradient is the partial derivatives of the all the input or all the depending variables, and at the time it will update the weight. So after every iteration, the weight are updated, and that is known as your back propagation are used for the training the deep learnings model. Okay, so this is your And this will non-aerial artificial neural networks. This is non-aerial artificial neural networks where my weight are updated at every iterations. Okay, so this is non-aerial artificial neural networks. Okay, and the back propagation is the optimization function based on your non-linear programming, minimize the loss function f, representing the goodness of the feed. Goodness of the feed of the prediction of the observation such as the sum of the square error is given by the this one. So there are the many model about the back propagation. One is the gradient descent optimization, first order, Newton method optimization, second order, or combination of the either combination of the gradient descent and the Newton method to get the update of the weight in every equations. Okay, so this is non-linear artificial neural networks. Now, how to train the artificial neural networks? Okay, so there are the in this case the training is done by the iteratives. Okay, training is done by the iterative. Every iterative the weights are updated by the finding the gradient of a loss functions. Okay, so that is a case about the a training about the ANN is the iterative optimization process where the network parameters are updated. So there are the depending upon the number of the input and number of the neutrons in the multiple layers. There are the many parameters. So all parameters are updated, and after each iterations, and one iteration is non-aerial epoch to minimize the loss function. To minimize the loss function. Okay, so there is a kind of the how the training can be done in the ANN. So there are the two way mainly batch training and the mini batch. Okay, so here what happened? What is a batch training here? Where each epoch, every iterations, entire batch of the training data are used. Okay, so there is a or M input or output said the it is used the as a training data in the mini batch training where at each epoch a subset of the training or incremental or online training based on a single training data sample chosen randomly is used. Okay, so this is your how the training can be done, and in the mini batches when you go for the measure the performance of the your DL algorithms. Okay, so at the time the mini batches will be useful to get the idea about the what kind of the performance can be performed here. Okay, so after the invention of the BP back propagation, the MLP multi-real processing is non-aerial universal approximation theorems. Universal approximation theorems. Okay, so what is this theorem say? In this case, we need the accuracy of the 100%. We need the accuracy of the 100% for any desired uh, uh, objectives. Okay, so now how we decide the number of the perceptions and number of the layers. Okay, so this is the case. It will define the within the single layer. Within the single layer, we can achieve the highest accuracies. That is defined by the universal approximation with only one hidden layer that produces a sigmoid activation function. That produces a sigmoidal activation function and a linear output layer that would be able to approximate any function with any desired level of the accuracies, provided the number of the hidden neutron is sufficient. Okay, so here whatever if you just go back here, so here if my neutron is a sigmoid function and my output function is a linear functions. This is my sigmoid function, and this is my linear functions. At the time, we can achieve the accuracy of the any detail level in this by using the single layers, but having the sufficient number of the neutrons. That is that is a non-ideal universal approximation theorems. Now, depending upon the input, depending upon the size of the data, I cannot take the thousand of the neutrons in a single layer. Okay, so this will give the idea about we can achieve the any desired accuracy of the any desired level by using the sigmoid execution function and the linear function within by the one single layers. The concept about the multi-layer processor is not needed. Earlier I talk about the non-linearity of the input. Okay, but now this theorem say within a single layer, I can achieve the accuracy of the any desired level with the help of the sigmoid function with the sufficient number of the perceptrons. Okay, so here the concept about the multi-layer is not exist, but this is a there is a question here why we need the multiple okay. Now, so this is a case. Okay, so this MLP is a permission class of the ANN, and the MLP is also known as your feed forward neural networks. Feed forward and neutron network. Feed forward is what? It input to output. There is no back forward. No output of the any layer is coming back to the input. So this is the feed forward neural networks. It is a building block for the other type of the ANN. So there are also autoencoder. Okay, this autoencoder is used for the reduce the dimensionalities of the your input and for the your feature learnings from the unsupervised learning to the supervised learning. Then the recurrent neutron networks, long short-term memory, and the convolution neural networks, and the generative adversarial networks. So these are the type of the ANN. I can say it is a type of the deep learning algorithms. Now, so this is known as your whatever in application of the ANN in the remote sensing of the environment, atmosphere forecasting, hydrologic modeling, it is a non-area Persian, that is the precision estimation from the remotely censored information using the ANN, Earth and environmental science. So these are the some of the area where the deep learning can be used. In early 2010, the third wave of the popularity and the interest in the ANN, this field revived and renamed as the deep learning. So this is a yeah. एक मिनट so that AC that fastball AC no गिरा तो that
Sir, in this slide, video mentioned the various type of vehicle line. So, in clearly in which side the presentation, you use my what are the differences between, for example, where I can use service case, or I can use
yeah I will tell them it's coming in my next slide. Okay. ऐसे तो बताएगा गर्मी पड़ेगी some of them I will discuss here not possible to discuss all one okay yeah it is coming so this is your auto encode this is your auto encoder deep learning method okay so what is the use of the auto encoder it will use to decrease the dimension of the input space. Here in the deep learning, the data size is very large. Okay, so whenever in this case, if you handle the data set, every layer of the same space, then it will consume the more computational power. Okay, so here in this case, what happen? Auto encoder What is the encoder for given input? It will decrease the number of the dimension of the input, and from this number of the dimension, this part it is a decoder. It will reproduce the output with the same as your input. Same as your input. The autoencoder is a MLB typically trained by the back propagation with the one of the more hidden layer that receive the input and aim to the produce the same input as its output. Okay, the middle layer has a few neutron, then the dimension of the input acting as a bottlenecks that encode the input data in the lower dimensional space and preserve the information contained in the input which is recorded back to the original input one. And here, uh, in the case of the your convolution networks, okay, so we are making the features extractions. Okay, so this is your we are reducing the dimension of the your original input data. So this is one of the way we can reduce the features size of the feature and reconstruct the features reduce features dimension from to the original input. Okay, the first input are reduce the dimension, and then after the from the reduced dimension again it is the same input are constructed. Okay, so that is the case about the your use of the autoencoders. Now, uh, now these are the number of the theory or number of the claim from the different kind of at context in the area of the uh, uh, deep learnings. So whether single layer or multi layers. Okay, so with the help of the what you call universal approximation method, single layer is enough. So why we want to go for the multi layers? Okay, so there are the many author and many researchers claim the Rajavi et al. In 2012 survey that the ANN application for the surrogate modeling in the water resources and reported that the 90% of the modeling has only one hidden layers. Okay. Tamura and Sasesi is 1997 favored the ANN with more than one hidden layers. More than one hidden layer and required fewer hidden neutron to approximate the same functions. At the same way, DBDS and Bernard 93 asserted that the single hidden layer ANN are superior to those with more than the one hidden layer with the same level of the complexities. So here it is a three general reason in the interest toward the ANN. The universal function approximates the theorem is provided the ANN are fully capable of running any function. The principle of the parsimony is the ANN with the fewer hidden layer are generally deemed less complex and more understandable. And the difficult of the training as the ANN with the more hidden layer are more complex to train. So there are the many kind of the discussion whether the single layer or the multi layers. Okay, and because of this, unsupervised learning was used to pre-train the deep double N. The deep is the depth number of the neutrons, and the width is the number of the layers. Okay, so that is given the idea about the from this concept. This field is known as your deep learnings. This is known as your deep learning based on the concept about the ANN. Now, what is the geometrical interpretation of the deep learnings? Okay. Now we know the deep learning are the black box. Okay. So if you want to understand what is the inside, what is the meaning of the interpretation of the every perception, then we may get the idea about the how, what is the how the training is going on inside the your deep learning algorithms. So now for this case, okay, you just consider the single perception with the activation function of the sinusoids. Consider the single perception with the single input. Okay, so here the output yr1 will be the x1 into the corresponding weighted plus br1. Okay, so this is your single perceptron, and whenever it is applied to the sigmoid activation function, this is my output of the this perceptrons. Now here what is my original data is the input, bias and weight. It is converted all this information into the this waveform. That is your sinusoids. Now here, this sinusoid function having the I can say uh, three variables here. Okay, the variable is the one variable is the height of the sinusoid functions. Height of the sinusoid function, which is given by the HR equal to W1 square R, the weight of the my perceptrons. And then it is the slope of the this sinusoidal functions. This slope is given by the W1 R2 and the WR1, the two weighting function here, and the distance between the this intersections from the origins, which is known as your dr distance. This is your minus br1 divided by wr1. Say so. This is in short your original input, your input x or and the weight and the bias are converted into the mapping into the this three variables h, d, and the s. S is a stroke, h is a height, and the d is the distance from the origins. Okay. Now in the same way, this is for the single input. Okay. Now so I can say single perceptron can be mapped with the this sigmoid functions. Okay. Now assume multiple perceptrons. Okay. So I will discuss now. In the same way, now another contributor, if the more number of the input, if this is case for the only one input, now if you go for the two input, what will be my sigmoid functions? Okay. So in this, sorry, yeah. So this is the case when my two input single perceptron with the sigmoid functions. So it is my sigmoid plane. Okay. So in this case, my sigmoid plane having the in earlier case it is three variables: h, slope, and the distance. Here it will consider the what you call angles. It is a consider the d minus 1 angles. D minus 1 angle. The angle is the this is your my angle alpha r. Alpha r is the my angles. So if you go for the two input, then it is coming the just 1 meter. So here it is the my another is the angle of the normal vector perpendicular to the plane. Another variable, and then it is the LR is the range of the vectors. So in this case, when the my input is the 2, yes, madam.
Yeah. Okay. Sir, like, job 0 to 1.
No, weight may be anything, madam.
So that W of to 0 was 1. Yes, right, sir. Yes. It's like a distance is not equal to minus 5 divided by the weight by you take a 0 20 40 weight. It is up to the once you get the distance near the x-axis of 5 x-axis.
Now, here the distance will be the infinite. Infinite. Distance will be the infinite. Your sigmoid function will be the very stretchable functions. So it is at the time it is a straight line, madam. It is a straight line. So at the time what happened? The your model will be the collapse. Your no, at the time the model will be the collapse. There is no importance of the model in your training set. Okay. Huh? I will discuss this point in some another way. So here, whenever it is a number of the input is a 2 with a single perceptron with a sigmoid activation function, at a time my sigmoid plane will be having the 5 variables: H, D, and the slope, and then angle, and the magnitude of the vectors, LR. So here it is a 5, what you call 5 variable mapping from the original input to the sigmoid. Now this will give the my output of the one perceptrons. Okay. Now whether my now input is a 2 to 4, if I increase the input, at the time my angle will be the number of the variable for the angle will be the d minus 1. D is the number of the input. D is my number of the input. So this is my one perceptron idea how my input will be the converted into the my sigmoid functions. Okay. Now this is the case. Okay. So we know one perceptron. Okay. Sigmoid functions. Okay. Now I want to rewrite the sine functions. I want to rewrite the sine function in the my single layer A and N. Okay. So how I can get? Okay. So here you can consider. So you just consider 3 perceptrons. You consider the 3 perceptrons are adding side by side. This is the 1, this is the 2, and this is the 3. All are sigmoid functions. Okay. And then it is the adding. Adding is for linear additions. Okay. It is a linear additions. So here this is the my this is the case. This is the blue one, green one, and the red one. 3 sigmoid output of the my this 3 perceptrons. And when you add, then you will get the this sine functions. Okay. So here what happen? You can get the this kind of the sine superposition of the this 3 sigmoid. You will get the this one. So this is my original signal. This is my original signal, break one, and by using the break function is the sine function, original sine function, and we want to estimate the same original function. So with this 3 sigmoid function superimpose, then I will get my output is my as the same as my input signals. Okay, so this is my we are come to near to the predictions. We are come to near to the predictions. Okay, so this is the case about the how this perceptron, or I can say deep neural networks, will come in the picture by superimpose the perceptrons in the any order, either in the side by side, or it may be series, or it may be the parallel. It will depend, and this will give the different type of the deep learning methods. This is known as your AWN. The how you connect the perceptron, whether in the series real, whether it is the parallel, then it is defined a different type of the neural networks. Okay, deep neural networks, depth neural networks. So there are the many cases in the case of the your neural network case. Okay. Now this is the case. Okay. Now this is the case about the input, 2 input. Okay, 2 input and 1 output. Okay, input is what for the data set. It is my features. Yes or no? Input is for features of my data set. Okay, so this is the output is it will give the by features either by output. Okay, so I want to approximate the this features in the my AWN model. Okay, so here what happened? So this figure is the objective in the 2 input problem. It approximated the DOM-like features functions. So how I can accuse? Okay, the first case is the 6B. Okay, so suppose import the 4 sigmoidal unit with the equal height, equal slope, and equal locations, distance, but the different angle 90 degree apart. The performance of this is not same as my requirement. This is my requirement, and this is what I superimport the four sigmoid functions with the same angle, equal slope, and different angle 90 degree. So I will get the this ones. So this is not a as per the requirement. I need the this one, but this is a I when I use the four perceptions. Now if I use the 8, so it is a as compared to this, the my it is a near it is a smoothing the my aging of the my requirement. Okay, so this is the my 8, and this is the case when I use the faulty sigmoid function, faulty perceptions in the my single layer. So I will get the near to the this ones. Yes or no? So here what happened? I am adding the perception in the my single layer. Earlier it is the 4, then this is the 8, and this is my case of the 40. And this is non-area. I can say it is a single hidden layer A double N. So I will get the, when I put the 40 perceptions in the one layer, I will get the output same as my requirement. Okay, same as a requirement. So this is my case about the what is called area universal approximation theorems. Yeah, yes, madam.
So, one of what didn't no number of units.
Madam, it is coming. Wait. Okay. So this is a one example. This is the one example. Okay. That's why I just make the my what you call single layer versus a multi layers. Okay. And we know the deep learning are having the multi layers. Okay. So this is just understanding about the fundamentals point of view. Okay, madam. So this is the case here. Okay. Now this is the case with the number of in the single layer with the enough number of the perceptrons, we can get the output same as what we require. Okay. So this is the case about the this case. Now what is the inactive input space? Okay. So if you just see for this example, okay, this edges, the corner edges are not come in the picture for the your making the decisions or making the prediction about the my original signals. So these are the input which are not using to make the predictions. Okay, these are the input space are not used, or I can say the features that are not contributing the enough to make the my decisions. So this is known as your inactive input space that will identify the my features, which features are important or contributing, or which features are not contributing in the my decisions. Okay, so this is known as your inactive input space is shown in the figure 6b when the corner on the input space do not show up in the data available. The for example, the hydrological example where where the snowfall and the temperature are the two input to the A double N. So in this case, snowfall never happen at the high temperature. So this is the my that feature is not contributing the either figures or either output. Okay. So here uh, ANN with the two hidden layers. ANN with the two hidden layer. Why more than one hidden layer is required, and how to reduce the number of the nuclei in the hidden layers. So here, consider the figure 6b. That is the for the your four sigmoidal unit and the cascading the second hidden layer with the non-linear activation functions. Now here is a case is what after this four sigmoidal perception layer, four neutrons, and then after the another layer is adding with the non-linear activation function. Earlier in the sine wave case, it is a linear superimposing. Now I am adding the non-linear activation functions. If you just go back, okay. in this case, this is my linear activation functions. Super important. Now I am adding the non-linear activation functions. Okay. So what is the non-linear activation function? It will after some threshold value. What is the non-linear? After threshold value, it has become the some particular line. Yeah. After the non-linear, it is remain the same. Okay. So it is I can say it is a cramping, or it is a normalized in the some particular level. Okay. So here with the non-linear activation function sigma for this case, non-linear case, I am using the sigmoid only. Okay. To depict the any feature that is under the threshold. And this sigmoidal function in the second layer bound the geometry which is shown in this figure. So what is the case? Earlier, we are using the linear combinations with the any number of the perceptron in the one layer. Now with the 4 perceptron, and then after the linear combination, non-linear activation function again. So my here what happened? This output layer, the output layer, or I maybe hidden layer, is also the sigmoidal. That is the power of the activation functions. So what is here? With the 4 perceptron in the first layer and the 1 perceptron in the second, are 8 accuracies of the my desired output as compared to the input. And that's why we are going for the multi-layers. That's why it is a multi-layer concept about the neural networks. Single layer is enough. But the here the now what is happened now? The simple case about the sine wave. In this case, okay, we require the 40 neutrons. Okay, now if the input are the very non-linear or maybe the quadratic, at the time the number of the layer are the more. Hyperparameter will be the more. Okay, in this case, with the sigmoidal function, we can make the having all parameter here in the case of the deep learnings. So that is the case about the. So now you get the idea. Multi-layer MLP, okay, and ANN, and why we have that multi-layer perception in the deep learnings, okay. Now conclusion is what? By 4 neutron in the first hidden layer, we can approximate any function similar to the single hidden layer ANN by putting the number of the dome-like functions side by side. And this is a non-linear deep learning or deep ANN. It provides the more flexibility while they may require the fewer hidden layer neutron across the network for representation learnings. Now, what is the issue here? When you add the multi-layers, you get the benefit. But there is the issue here. The issue is the vanishing and exploding the gradient. Vanishing and exploding the gradient. Whenever I go to the every iterations, my weight are updated by finding the gradient of the my loss functions. Okay, so at every iteration, what happen? My some gradient are converse, and some gradient will go in the that is the vanishing and exploding. Vanishing is the going to the diverse, converse, and exploding is a it is a diverse from the your diverse in the case of the gradients in this case. Okay, so this will provide the those who are vanishing, that feature is 0. Okay, when those who are converse, then this feature will be having the more weighted. Okay, so this is the issue in the this model multi kind of the MP having this kind of the problem that will affect the training, that will affect the training models. In this case, what happened? some feature are varies, then it will not come in the my training in the modeling of the training of the models. And some feature are the having the more weightage, then it may be the biasing also sometimes. Yes, madam.
So I should understand why should we go with this vanishing and exploding variables? Because for each and every features, how to modify the value of the W? We have a new value of a W, is nothing but old value of a W minus some learning rate, and we take the partial derivative of error or cost function with respect to the W, right? So for each and every iteration, we consider the previous value of the W and we calculate the new value of the W and we multiply it with the learning rate. So if we take the small value of the learning rate, then definitely we have the proper local and global minima. So I don't understand why should we have this exploding gradients issue.
Gradient is giving the divergence of the my gradients. At the time that it is giving the maximum rate of the increase of the this states. And this is happening in the because of the there are the many number of the neutrons, many number of the weight, the parameter are more. So there are the some case where the my gradient are explode. At the time the my input that part of the my input will be the having the more weighted in the my training. Like this way I can give the answer, madam. Okay, there are the many it is not one or two number, okay, but there are the many number of the neutron. So there is a possibility coding. Because of this our training will affect, because the vanishing the feature will be the zero. So at the time that for me if this feature is important and it is vanishing, then my training is not proper.
Sir, my question is regarding why should we have this vanishing and exploding gradient issue? Because what I understand that my gradient descent curve is like U, right? So for any random initializations value of the W will have the curve like here. So ultimately the error value is at the peak. For each and every iterations, we are just decreasing it with the partial derivative of the cost with respect to the W, right?
This happen to
With respect to the W. W means our parameter. So it's nothing but rate of change of W. Our goal is to minimize the error. We need to find out the values of the W in such a way that predictive value of the ANN algorithm and actual value should be same. So error is minimized. So that is why we are taking the rate of change of error with respect to the rate of change of W. So if we take the slow learning rate, like very less value 0.00001, in that case, suppose initially we are at the peak, it means for given W, error is very high. Our purpose is to find out the point on the curve where the error is zero. So if we have the very low value of the learning rate, then gradually we can go to the down where we have the global minima. And once we reach at that point, it means we have arrived at a point where we have a good value of the W for which error is not exactly the zero, but very nearer to the zero. So when we take a low value of the learning rate, we get the our algorithm should be converged. Now you're talking about vanishing and exploding gradients. It happens. What I understood, it happens when we have the high value of the learning rate, wherein it will jump from one point of the curve to the another point, and it will not go out and it will not reach out to the global minima point. So is it like that? Because what you are suggesting that due to the W, we are putting if value for W is a zero, it means there is no significance of the feature, because ultimately we are multiplying W with the input X, right? So if but value for W is a zero, means there is no any significance of a given feature. So it may happen that though the certain feature contributes a significant role for making the decisions, and due to the value of the W, the overall value will be zero.
now, madam, I just want to give the idea here. If you just see, okay, Now, for this case, this suppose W1, the weight update in the equation, it will update based on the partial derivative of the others weight also. Okay, this W1 is not update only one variable W, but it is also updated because of the others weight of the your structures. Okay, so there is here what happened in the when you finish the one iteration, at the time it is coming the probability mapping. Okay, so at the time what happened, there is some possibility that the some weight are having the more weighted or more weight. I cannot more dependency or less dependency. And when you do the partial derivatives, so at the time at the time there is a possibility of the some weight are zero or it may be the maximums. And whenever it is zero, at the time the suppose if you just say this is the zero in the second equation, at the time that input will be the no contribution in the my iterations. There is the many things. And whenever exporting it, at the time it is the maximum value of the weight for at the given of the time. So at the time the others weight are not having the much important in the my decision. So that is the case about the vanishing and the exporting about the because of the gradient nature and because of the probability distribution of the every equations. This will give the one issue in the multi-layer multi-layer perceptrons. Okay, so that is the case here.
When we say like we not find error from minimum, and where the function is going to follow the basic behavior, then gradient will go going what?
Available. I will relax this.
I'm waiting for hours. So question is that in that diagram, can we see like that when gradient is going to vanish, that means errors are going to nullify by the computing in the multi-layer. 1 layer, 2 layer, whatever the number of lectures are there, gradient is not there. What madam is saying, even why it is going to vanish. So we are going to follow our accuracy more.
Yeah, when the gradient is varies, at the time the particular weight will be the near to the zeros, and that input I just told here
Will be zero when we are getting a better value, when prediction is good, when function is full.
here, madam. For example, for this input, okay, for this input, the particular weight will be the varies. Okay,
Is that is right, but when you
what input will be not contributing in the my decision, and then the my error will be the more in this case.
but we are saying that vanish. So what is the implied meaning? Our algorithms good or it is doing bad? Or our algorithm is performing good or not performing good? That is my question.
Whether it is vanish or exporting, in the both the case, your performance is not good. At the time the loss function will be the more.
So we are going away from the prediction.
Yeah, it is the loss function is a more meaning is a predicted value and ordinary value having the more
Difference is
yeah. There is the problem in the this case a double n when it is any weight will be the vanish or exploding. At the time the dead feature are nullified
So then,
and the loss function will be the more.
then for vanishing and exploding, so both the phenomena might not be same. Na? That might be.
What's the difference?
Yeah. So that
There is the possibility of the some weight are vanishing and there is the possibility of the some weight are the exploding.
okay. Fine. Thank you, sir.
Okay, so this is the issue in the yes. This is the issue in the ANN. The having the during the training. Okay, some weight are vanishing or exploding. Now, how to solve this? Okay, how to solve these issues? Okay, So, so this is I will discuss the solution in the next part. So before this one, there is this is called whenever vanishing or exploding. At the time, it may be the underfitting, maybe the overfittings. When my gradient is vanishing, every time my training will be the underfittings, and whenever it is the exploding, it is overfittings. Okay, so we want to stop this phenomena. Whenever the gradient will be the vanishing or exploding, every time that we want to stop our training model. Okay, then and then only we can find out the good training good better loss function, or I can say better predictions as compared to the original requirement. Okay, that is the case. Okay, so there are the many issues here. Okay, so here this is the just for example, what is the Occam ledger? The Occam ledger and the equipment finality is when you have the simple solution, why we go for the complex solutions? If you have the simple solution, why we go for the complex solutions? Okay, earlier it is a single layer with the enough number of the perception. So why we are going to the multi-layer MLP deep learnings? Okay, so this is a non-area deep learning is a relevance to the open ledger, not following the simple solution, but the complex solution because of the others advantage which is not happen in the simple solutions. This is the ANN with the 2 hidden layer with the 10 neutron in each layer, 71 tunable parameter in the first hidden layer, and the 110 tunable parameter in the second layer. Total is the 181 tunable parameters. And in the second case, with the linear and quadratic regression model require only either 6 or 21 tunable parameters. So here it is this is a non-area Occam ledger principle require that is giving the solution in the simple way, but we are using the complex solution with the more number of the freedoms, more number of the parameters. Okay, that's why the deep learning is against the Occam ledger Occam ledger principles. Now, what is here? This is a hyper flexibility in the fitting of the data owing to their enormous degree of the freedoms. Okay, parameter 181. If the parameter, then the complexity will be the adding. Okay. Now, overfitting the solution with the model fit the noise in the data rather than the underlying function. And the lack of the generality is the model does not poorly out of the sample prediction that is the predicting the situation in the data used for the model training. So this is the out of which is not considered during the data which is not considered in the training. If you perform after the training, then my model will be the well trained. Okay. So now, whatever the vanishing and the exploring the gradient, so we want to make using the early stopping criteria, or you have to regularize your trainings. You have to regularize your training by using the identify where I want to stop my trainings. Okay. Yeah. I'm. It will take this. We have to find out. We have to find out where to stop and when my gradient will be the vanishing or explodings. That we have to find out by looking to the number of the performance metrics. Okay. Now, how to control the hyperflexibility of the ANN. Okay. So in the generally what happened in the training. Okay, in the training of the your model, we are dividing the data set into the two parts, training and the test on a in the case of the ANN, your data sets are divided into the three parts. Training, and the same way the calibration data set in the traditional modeling, then it is the validation and the testings. So this testing is the same as your validation data set in the traditional modeling, and this is the second part that is the validations So used to control the flexibility of the network while training. So if you divide your data set in the three parts, then and only you are able to find out the where to stop, where the vanishing and exploding will be occur. Okay, so here the, in the AAN we are dividing the data set into the three parts. That is that will help to find out the early stop criteria. Okay, in this graph, okay, this graph is what the error function and the number of the iterations. Number of the iterations. Okay. So generally, what happens if you increase the number of the iterations, then the loss function will be the decreasing. Okay, these are blue lines during the trainings and during the validations. What is the validation here? Validation is not a same as your validations. Okay, so, here this validation is not a testing data set. Here validation is used to reach the hyper flexibility of the network while trainings. During the training, we are doing the validations. During the training, we are doing the validation of your models. So here, in this case, at the time during the part of the training, if you validate the model, so at the time initially when you increase the number of the epoch, at the time my loss function will be decreased, and then after it will my error function will be increased in the case of the validation in the training part of your models. So this time we have to stop the trainings. At this number of the iteration, we have to stop the training. So what is happening at this time? It is happening the increasing all when my loss function is increasing. What this meaning is my loss function are increasing. So what is the meaning? Some feature are major contribution or minor contribution in my predictions. So at the time my error will be the more, and even though if you increase the iteration, at the time my error function will be the increasing. Yes, madam.
For a given data set which by its their payment sets, validation set, and place set, right? Now we when the suppose we go with the random sampling method. It's okay. Yes. Oh, sorry. So here we have divided our data set into three sets, right? Training set, testing set, and validation set. So if we go with the random sampling theorem, wherein we can select the samples randomly for the training set, data testing set, and the validation set. Now, in this graph, wherein we need to find out the point where the training error starts decreasing and validation error starts increasing, and at that point we should stop learning the mod, right? So if we go with a random sampling for selecting the validation set of the data, training set data sets, and the testing data set, so don't you think that we will have the different point? Because validations, whatever the samples the validation data set included in this case,
Madam,
samples would
your
be
question is the how to select the validation data set.
no, sir. That is not my question. My question is like there should not be a single point wherein our validation error
So
starts
it's not single.
increasing.
This is not single point, madam. This is not a single point actually. It is a number of the equation here.
Yes, sir.
5, 6, 10, 9, 10, 11. So after the 7 and between, it may be the case where my validation error will increases. So only up to the 7 iteration, I have to make the training is enough.
No, sir. My question is like, ultimately we are doing it for the same data set. So why should it like when the error is decreasing on the training set, error is increasing on the validation set?
But I told you, madam, AAN having the issue about the variation and the great
No, sir.
And because of this, if you increase the equations, even though my some features are the weight of the feature will be either vanishing and the exploding.
No, sir, what I can draw the conclusion from this graph is like validation set contains those samples which were not included in the training set.
Yeah, that is okay, madam. That is okay.
Otherwise, sir, if that mimic set works in the both training and validation set, then perfect cannot be these equations like this.
No, madam, you are making the confusion here, madam. Here, what happened? This is a ordinary case when the traditional training models. This is the case about the traditional training model, and here it is the training set are divided into the one is a training and second is a validation. Validation during the trainings. Okay, so at the time at the time we are identifying the when the vanishing and the exploding is occur during the trainings. At the time we want to stop the training.
Now, sir, suppose there are 100 samples in a data set. So, what we generally we use 60% data for the training samples, 20% for the validation, and remaining 20% for the test data set. So, if we have the curve like parabola, that is blue line for the training set, and that is why I'm saying if the 40% of the samples for 50% of the samples of the data, if the curve is decreasing, it means error is decreasing, then why should we have the error? Okay.
We are not, this is a black box. Okay. So it is very difficult to get the which weight are vanishing and which weight are the explodings. Okay. So this is a case. We just come across when the my error will increase. Generally, error are decreasing, but when it is increasing, meaning there's something wrong. That the some feature are not come in the picture for the prediction of the my data. By the time my error rate are increasing. And that is the case about the vanishing and the exporting the variant only.
Oh.
Okay, so this is a case about the this is a now at the time if you go beyond this point, at the time it is the overfittings. If you go above this point, if you still it is the say it is the overfittings. And it stopped my stepping before this point. At the time it is the underfittings. Okay. And at this point, we want to identify, at this point, we will give the identification of the, to stop the training. So that is your early stopping training. Now, your data is still available. Your data is still available. So we want to find out whether this training is enough for my prediction or not. So for this case, we want to test, I can test your out of sample predictions during the when you stop the at this point. So this is your out of sample prediction on the testing data set. Okay, so here we just want to get the idea about the underfitting, overfitting, and then also we can get the idea about the when to stop the training. And then after when you decided this one, then we want to go for the out of sample predictions during the your testing data set of the your your data set, original data set. Okay. Now another is the back variations. Okay, so this is the second way to solve the issue of this is your regularization of the your. This is the your techniques to control the flexibility of the A-double-N, try to minimize the regularization function during the training. During the training to control the A-double-N flexibility and tailor it to bottom at the hand and smoothing the response surface. We are talking about the smoothing of the this age. Okay, if you smooth more, then it is this is the regulation of the your uh, during the platings. Okay, so this is your traditional regulation function is the sum of the square of all the networks parameter that need rest activity on the left cone and connect bring the rest. Square of the all the strobe of the sigmoidal unit that target and remove the unnecessary feature which are unsupported by the data from the overall network response. Okay. Now this is the case about the how to regulate. Okay. So this is my the dotted line. Dotted line is represented the my sample data sample point, and the red one is my a double n, and this is the my underlying function that is required. So this is the case about the when it is all fitted. This is the case about all fitted. Here we are adding the regulation functions with the minimum value of the uh, uh, what do you call. So here the regulation function is added into the loss function with the minimum minimum regulations. And if you increase step by step, then the my overfitting will be the control. Then the overfitting, or I can say vanishing or exploring the gradient will be the control by adding the regular what do you call regulation function into the my during the trainings. And when you increase and when you come at this point, then my model will bring the design of output as per the original one. And if you stay in with the give the more regulation function, then the my A double N output will be the 0. Then there is no what do you call no effectivity of the A double N model when you increase the give the more weightage to the regulation functions. So this is a way to solve the issue about the A double N either through the regionalization and okay. So this is the one of the way to make the solve the problem about the A double N. And third is a third techniques of the regulation is a dropout. Okay, it is a dropout. Suppose this neutron are vanishing. If this neutron are vanishing, then you drop this neutron into your network. If this neutron is exploring, then you drop out this neutron from the your deep level neutron networks. Okay, so these are the case about the dropout and the this in the case of the A marine. Okay, so these are the now the rocker is a representation will they consider as a machine learning, and the distribution representation is a my deep learning method. Okay, so these are the thus a difference between the deep learning and the deep learning and the machine learning. So the transparency is more in the case of the local representation, and the transfer is very complex in the case of the deep learning. Learning difficulty in the it is easy to learning and it is a more difficult. Network size is depend upon the directly proportional to the size of the data set. Number of the processing unit mirror the number of the training data sample intractable in the presence of the large data set. Limit of only 400 sample point for the user for the use with the Gaussian emulator machine. A smaller network size of the network depend on the trajectory of the feature in the data set and easier to scale, and the inaccurate interpolation of the information and number of the output. So this is the just comparison about the Docker representation, that is the machine learning, and the distribution representation is a deep learning point of views. Okay. So here number of the output in the machine learning only one output, and for the second output we have to train the again. Okay, but here it is a multi-output model. Okay, so this is the advantage of the MLP. even though it is a complex, we have to opt for the A level N I can plug model into the my prediction model of the AI. Okay, so this is the case. The multi-output, because of the multi-output, or maybe there are many advantages here as compared to the local representation of or either in the machine learning point of view. Okay. Now, up to now, we didn't discuss about the time dependency of the data. Okay, it is a static data. Whatever the data set, it is up to the static data set. Okay, now how to introduce the time dependency on the data sets. Okay, and that is given by the tape delay lines. This is a non-area tape delay line because the time dependency previous data data of the previous times. Okay, so this is non-area tape delay line. So at the time that this delay will give the delay is what? It is a memory. Delay is a memory. Okay, so it is a time dependency and the memory in the deep AAA. So here this is non-area adding the if the my data of the time dependency. And for this get we have the need to require the tape delay lines. Okay, and this is the model input and the X of t. Okay, between the your perceptrons, we are adding the time delay unit, or it is I can say it is a memory. Okay. Okay, so this is a non-linear time delay neural networks. Time delay neural networks. Madam, जो आपका तो question था ना तो yeah. So this is your time delay neural networks. At the time the output of the perceptron is the delay with the input of the any layers. Input of the any layer. So here what happened? The it is now back propagations. Feed forward and feed backward. Earlier it is a feed forward only from the input to output. Now it is the out to the input. So it is a backward. Okay? With the time dependencies. Time dependency, and that is known as your time delay neural networks. Okay? Yes, madam.
એમ ઓલ કરી દો એલજી એઈડી બંને રીતે.
Now, sir, I have two questions. First is, generally we see that the deep learning algorithms runs faster than the ML algorithm, right? In ML, we are using the same structure that we are using in a DL, except that we have one upper of neurons and one upper of the hidden links. Though we have experienced the much training time on ML algorithm rather than the DL algorithm. So, what are the reasons behind it? And second question is with respect to this time delayed neural network, where in the input of the neuron is given as an input to the delay unit, and finally the delay unit is given to the input to the next neurons of the next layer. Then what is the functions of the neurons of a given hidden layer? Would you please show me that slide, the delay time delayed network? Yes, sir. Next slide. Yes, sir. So in the first hidden layer, whatever the input goes to the first layer hidden layers, we are just giving that to the context unit. That is nothing but the delay.
Here the madam that equation of the perceptrons, sigma of the Wi into xi.
Plus PL.
Xi. So here it is a time. Here it is there is no time. Well, adding the my time. So x of t minus 1, or it may be the w of this one. So there is a change in the your equation. So
Sir, would you please show me that slide? Now my question is not regarding whether we are using it for the time real-time application or not. My question is regarding the neurons of the first hidden layer. Now, what kind of the function is being performed in these neurons of the first hidden layer? Because we are not doing anything with the output of the neurons. What we are doing, whatever the inputs is given to the neuron of the first hidden layer, we are giving it to the context unit and we are taking it to the next layer. So, what kind of why do we need the neurons over here? Because ultimately we can provide the input directly.
No, madam, suppose for example, temperature. Okay. So it is a T equal 0, T equal to 1, 2, 3, 4. So there is some kind of the one data set on the temperature is based on the time. How this can be incorporated in the deep neural networks. Okay, so this is a way to include the time dependency of the data sets into the neural networks. This is just one example of the how it can be the with the output of the one processor is connected with the input of the this processor. So there are the many possibility of the connecting the time dependency of the your data sets based on the different kind of the connections. It may be in the same layer, it may be the into the different layer. Suppose what happen, the every time step, all the paths are updating. But in somewhere it is after the 5 time step, it is updated. Every time that input is connected to the fifth layer of the my hidden layers. It is depending upon the what kind of the dependency, time dependency are on the your requirement. Based on this, we have to make this kind of the structure into the your during the implement of the this kind of the requirement.
For example, a time relay neural network that we take an example of real-time video streaming applications, which is actually very time-bounded applications. Because what we can say is that the where relay data is was than the bad data, right? So, for example, for this kind of the applications, how do we utilize this real-time neural net? I mean, timely delay neural net.
No, madam, I cannot give that answer right now. Okay, the for specific, I just give the idea about the how the time dependency can be incorporated into AWN. Okay, that question can be addressed in the some another my lecture because I just want to talk about the type of the fundamental of the deep learning right now. Okay. Yes, madam.
Ma'am, एक minute. रुकने चाहिए.
If I have a sequential data, that means the data itself has a one delay unit. Means one current sample is there, the one previous sample is there. So can I use without a delay block those both samples and consider those samples as a short memory? Short memory.
This is a short memory kind of thing.
So is it? Am I understood the right?
Yeah, this is the thing upon the I told me short memory and the long memory dependency.
Yeah.
Okay, short memory is within the next sample there is a dependency, and long term dependency is after the 10 step of the my output is depend upon the after the 10 step of the time. Then it is the long term dependency of the my data. So there is this kind of the no. If you have the short term dependency, then you have to connect the current and the previous. Okay, and whenever it is long term, it is the current and the previous 10,000. So that is the long term dependency of the my data. So that is the concept about the short term and the long. And the short, we require the less memory. And the long term, we require the more memory. So it is the size of the memory requirement into the my neural networks. So there is a non-linear RSTM. If your data set is dependent upon the both short term and the long term, then it is a non-linear RSTA, long short term memory concept. And there is another type of the deep learnings.
So long short both is a if it's combined then it's a
RSTA. This is non-linear. My next part is coming, Vinam.
so if I have a sequential data and if I am using both the samples, for example current sample and the previous sample, then it is called a short memory.
Yeah.
And then at that time I don't have to add the delay block.
Delay time is required. Delay is required because the short dependency of the times. current and the previous. So one delay unit is required.
But if it is itself a sample is delayed by
No, madam. In the ANN, if you just look at the ANN, at the time there is nothing to previous and the current state of the your input.
okay.
Okay, at the time there is no delay. Only the data are coming and it is the processing inside the this one.
Okay.
Okay, get the point.
Yes.
Huh?
Okay.
Then if there is time consuming at the time we have to add the delay.
Delay block.
A delay in the what level? In the input, in the first layer, in the hidden layer, or it may be output. It's depending upon the your requirement.
Okay. Done.
Okay, madam.
Changes.
Okay, so here what happened? The number of the my tuning parameters is increasing depending upon the number of the delay unit. Okay, so that is the one question here. Okay, my tuning parameter will be the increase. Now this is your recurrent connections introduction by the John. So here a recurrent connection enable the ANN to account for the time evolution based on the increased memory concept, theoretically unlimited length, and is highly context dependent. Recurrent connection receive the output of a layer at the every time step and feed them back to the same or some other layer. So this is a figure about the recurrent neural network. When the one hidden layer, one output of the layer is connected to the others hidden layers. Okay, this is known as your recurrent connection, or I can say it is a recurrent neural networks. Okay. So I will just talk, this is my wrong short-term memory. Wrong short-term memory. In the short memory, for time dependency, it is the spot I can say neural networks. The dependency of time is the short, and whenever it is the dependency is the more, that is the long-term neural networks. And if the your dependency is both either short or long, then it is you have to use the wrong short-term memory. So in the wrong short memory, what happen? Some gain are those who are having the short at the time the number whenever you are talking about the short term memory, and if you have the long term, at the time we have to add delete the some gate into the your structure. And whenever you are working with the long term, at the time you have to delete your short term gate into the your this LSTM structure. So here the 4 input of the current time step and the 3 forget factor to be multiplied by the 3 context signal and the 2 output of the previous time step. So this is my forget gate and the gate driver, and based on the context signal, the dependency of the time short term and the long term be decided by the this context signals. Now I will take the one use cases here. Okay. So here it is a cases of the experiment use of the hydrologic system of the Oddman River watershed in the Canada, and the watershed having the area of about the 1434.73 kilometer square with a long average temperature of the 2.2 degrees Celsius, received the 611 mm of the precipitation, then include the rainfall and the snowfall annually, and generate the 11.7 meter cube per second river flow. Here it is used the 30-year long data. Data set is by 30-year long data of the different parameters. What are the parameters? Parameter is the flow of the river, temperature, snowfall, rainfall, and the total precipitation. In this case, what happened? This 30 year is divided into the calibration and the validation. So here, out of the 30 years, 22 years are used for the calibration, and the 8 years is for the your validations. and we are comparing the different kind of the model by using the LSTM and the HBV. HBV is the model given the my outputs based on the principle of the physics. Okay, so this is an LSTM is based on the your data set. So this model output will give the based on the actual principle of the hydrologic systems. Okay, by the scientists. Okay, but here and at what do you call, at the deep learning point of view, by using this data set, we are making the prediction of the my flow of the water in the my rivers. Okay, so here it is a case about the uh, uh, so here it is a case about the uh, training, testing, and the calibrations before the overfitting and after the overfittings. Before the overfitting and after the overfitting. So here during the training, training, what happen? This is the one will indicate the good trainings, and the before less than the 0.7 will indicate the training is poor. This is the non-area goodness of the field NSC. So here what happen during the training? It will show this is the value of the my goodness of the feed, and after the overfitting, the same will give the more value about the NSC goodness of the feed. So this is the advantage over the when you go before and after the overfitting. At the same way during the testing of the data. At the time, this is the value about the my goodness of the feed, and this is the value about the goodness of the feed during the after the overfitting. So after the overfitting, the testing is not good. Testing performance of the testing is not good, and during the calibrations before the overfitting, these are the my value, and after the overfitting, these are the my value. So here the testing will be the poor in the case of the after the overfittings. Now, in the same way, what happen here? It is the calibration performance. So you know that your data set is divided into the training testings. So here the before the calibration and after the calibration. So as compared to the HBV, the standard LSTM give the better value of the goodness of the feed. Okay, here the standard values are goodness there, and the process info LSTM is the what during the training at the physics of the product segment. Then it is a non-area process info process informed LSTM, and at the time it will give the good calibration performance and the valuation performance. Okay. Now this is a case about the when you go for the out of the sample predictions. This is a case of the out of the sample predictions. What is the out of the sample prediction? If you just see your unseen data set, at the time what happen, at the time how the model will react. Okay, so here what happen, if you just see in my data set, the value of the temperature in the water set is a 2.2 degree. 2.2 degree. If the because of the global warming or global climate change, if the temperature is increased from the 2.2 to 4.2, so how this is my unseen data, which is never happened in the history. Okay, history of the 30 years. So that is the that kind of the valuation is done by the this kind of the performance. So this is my observer data without the in the normal conditions. So this is the performance of the year average flow over the time of the years. At a particularly one period of the month, it is having the highest flow of the waters. And whenever the 2 degree Celsius is increasing, at the time the my what you call as compared to the HBV, this LSTM and the LSTM process are giving the better output as compared to the your HBV class model. So this is the benefit about the what you call LSTM kind of the model. When you see the out of the sample data in your in the your during the your deployment of the model, so at the time that you will get the better results in the case of the LSTM model. Now this is this idea about the if you now in the deep learning what happened, we are not concerned about the what is the physics behind the my data set. Whatever the data says, we are putting the training and getting the output. Okay, but if you add the physics, then the maybe the my training or maybe the validation will be the better as compared to the without the adding the physics. So this kind of the thing is discussing giving a completely better output in the case of the process informed LSTMs. Okay. This is a conversion and neural networks. How this is happening to feature extraction. Okay. And did you put in input my less dimension of the features to identify my filtering, or I can say it is a different kind of the reduction in the dimensional, and there is a pooling of the data. These are the applications of the CNN, and these are the different model of the CNN are used in the image processing or image predictions. Okay, so this is the year from the 1998 to the year 2022, different model based on the CNN. Okay, for the different kind of the applications. Okay, so this is the any question? Okay, so we will take the break for the 10 minutes and then we continue with the next lecture.
Thank you, Thank you, Professor Gautam Makwana, for sharing your insights in this enlightening lecture. We will now take a short break of 10 minutes.
Yeah.
After the break, we will move on to Lecture 8 titled Role of LLM and Data Analytics in AI ML, which will also be delivered by Professor Gautam Makwana. Thank you.
Go on so much. Anyway.
Yes.
Reduce some the size.